Let's talk about the algorithm known as the knapsack problem. This algorithm is very famous, and the main reason why is because of its utility. Suppose that you have a business selling chocolates during Easter, which is actually what many people do. Or if not, basically you have a business where you have to deal with multiple items and you have a particular measurement that is going to be your target. That measurement, that could be in kilograms or milliliters, represents the limiting factor for you to create different combinations of the different items that you have. So in this factory, you have to finish 1,200 milliliters of chocolate that you know, or your data shows that you're going to need to use during the season. On average, that's what the clients usually spend. So that's what you order. And as you probably know, chocolates come in waffles, so you need to melt them down. And the product is rather expensive if you want to keep it with good quality. So here you have 4 different molds. And the question is, if you don't really care about the identity or a particular number of each of these molds as a base, in how many different combinations can you add up the different molds in order to reach out 1,200 milliliters? These units, by the way, are given in milliliters. So that is what the knapsack problem tries to address. There is a vast number of potential combinations of these different molds in order to get a final result, which means that there could be more than one global optimal solution. During the problem of the troubled salesman, we identified the problem of visiting each city as a permutation problem. Here we have a combinatorial problem. So let's take a look on how we can implement this algorithm. The information that enters our algorithm is as follows. The first one, called epochs, represents the total number of times that we're going to try to find different combinations of molds that, when added together, reach a weight or a measurement that is as close to the target as possible. Iterations represents the total number of trials, local trials that we're going to take by looking into a particular mold and putting it or try to put it inside of the list of that candidate list of molds that whose added weight will try to match the target. 2 things would happen in that particular scenario. During the iterations process, you could either find a mold that overflows the container, in which case you don't add it anymore. But nonetheless, you still add 1 to the iterations. And the reason why we do this is because if at some point there is just no possible solution out of these molds that could not overflow the container, then you want to make sure that you are not stuck in an infinite loop. So that's why we add the iterations. We try 1,000 times, and if after 1,000 times nothing happens, then we finish that local search. So the next one is going to be a compound data type of type dictionary that represents the identity of one of the different molds. Notice that in this particular case, each of the molds is referred to with a letter in alphabetical order, A, B, C, and D. So this is one of the keys, the name of the item. But the second one is the information that will allow us to evaluate what is its contribution to a candidate container. These are the same values that we saw in the diagram of the molds. The next one is going to be the list of available molds. So these 4 elements are going to be nested within an array. And this array is going to be the one that we're going to be sampling during the implementation of the algorithm. The next element is going to be the target. The target is going to be the final amount that we need to match. In this particular case, that is what determines how many molds we're going to need to add inside of a candidate container. The target represents the amount of reference that we need to try to match by the addition or accumulation of the different molds. The next one is the list of molds. This list of molds is going to be the array on which we're going to be adding components, particularly molds, so that we try to get as close as possible to the target. The next one is the best of this list of molds, which is the same data type, is also an array, but is the one that represents the best solution so far. The same happens with the volume. The volume is going to be a local variable that is going to get redefined every step in the loop. that starts at 0, and as an accumulator is going to be adding to it the total amount of volume that we're going to use to compare with the target. In the same way, we have a best volume, which is going to be the best candidate so far that belongs to the best list of moles. And finally, we have the count. The count is going to be the variable that is going to tell us when the 1000 iterations are done. Every step in the loop, whether we have a success by adding a mold or a failure, quote-unquote failure, by not adding a mold, we are going to add 1 to the parameter count. And eventually, it's going to reach 1000. So it really is whatever happens first. Either we fill the container or we run out of iterations. So let's move into the implementation. We're going to start by first working through one single cycle. We're going to start with a while loop. And this is going to be a compound condition with two relational expressions. The one on the left is going to use the volume. And we're going to ask if the volume is less than the total amount or target amount. If the answer is yes, it means that we can still keep adding molds to this list of molds. The second condition is going to evaluate whether or not we have run out of counts. So we're going to ask if count is also less or equal to iterations. If the answer to both questions is yes, then it means that we can proceed. The first thing we're going to do is to pick a new candidate item from the list of items. Notice that at the beginning we imported the random library. Here we're going to use it to randomly pick one item out of the list of possible molds to pick from. So the candidate is going to be equal to a random choice. A random choice that is going to take from the available molds. Remember, the items inside of the available molds is a dictionary that contains two items, one string with the name of the item and one integer or float with the amount that that item contributes to the volume in this case. What we need to do now is to evaluate if the weight of this candidate, this weight, is added to the current volume is less or equal than the total amount for this container. If the answer is yes, then we can add to the list of molds using append the candidate. And we add to the volume registered so far the value of the candidate's weight, which I guess in this case should be the volume, not the weight. Let me change that real quick. Here we are. It's just that the name of the key was weight instead of volume. We're talking about milliliters here. Okay, so we have the particular volume of this candidate added to the total volume so far. Then, as previously discussed, regardless of what happens, whether or not we add this particular candidate, we're going to add one to count. Once we are done with this entire step, we're going to ask if the volume that we have in this particular cycle is bigger or equal than the best volume so far. Remember that we want as the best solution there, the one that approximates or equals the target amount. So if the previous volume was less than the current volume, it means that our current volume is a better hypothesis. So we're gonna take the best volume and we're gonna make it the volume. And we're gonna take the best list of mold and we're gonna make it the current list of mold. That's it. The next thing we need to do is to make sure that we run this for as many epochs as necessary. For this, we're going to add a bunch of spaces. Starting in this line, 57, we're going to add a for loop that runs for as many epochs as we need. At the beginning, we're also going to reset the value of the count, list of mold, and volume to 0, because these are local variables that have to be refreshed so that we can start with them and so that we can use them from scratch every time that we run this while loop down here. Because of the nature of for loops, we know that there is no infinite loops in here. So if we run the while loop properly, we are guaranteed to eventually exit the algorithm. Remember to always be careful with the while loops. Make sure that you have your updating step for your control variable, which is this count right here, and that you also initialize it every frame, right? So this line right here is very, very important because otherwise you either not enter the while loop or not exit the while loop. Okay, so now that we evaluate it, this should also be inside, is part of the process. Let's print out the information that we have generated at each step of our for loop. Here, let's just print the volume, and let's also print the best volume. Let's run our interactive window, and here on the right, we're gonna see the results. So as you can see, the different values get really, really close to the target amount, which is 1,200 milliliters. Actually, some of them get particularly close. So close that we wouldn't really care about losing that very little amount of chocolate. So you can see why these algorithms are powerful. They provide an application on how to work the least wasteful as possible. So let's just print the best volume this time, and let's see what we get. It seems that the best combination available with 100 epochs is 1,199 milliliters. Now, the last thing we need to do is to extract the molds and the count on how many we need of each kind. There is multiple ways to do this. However, it's just a matter of traversing the array best list of molds and then extracting the name of the items. So let's do that, and we're gonna do it with list comprehension. First, let's sort the list. That makes the process of counting easier for the program. And what we're gonna do is to join with a comma the elements inside of a list. However, keep in mind that the list of mold is a list of dictionary, which is a compound data type. What we really need to do is to extract the name of the items, that is the key called item inside of that dictionary, which is right here. It's called the item. So that's where list comprehension comes in. First, we're gonna add the square brackets, and then we're gonna ask for the mold at the key item for every single mold in the best list of molds. Now this is going to give us a list of strings. So let's sort it out. Now that it is sorted out, we have elements, we have everything separated with a comma. Let's print it out so that we can see how it looks like. We run this. This is what we get. You can see down here the different combinations of letters all sorted out from A to B to C to D. Now it's just a matter of counting them. For every single item in the arrange A, B, C, and D, we are gonna print the identity of the letter followed by a comma, and then the total number of times that that letter has been found in the list sorted LST. Sorted LST dot count, and then that item. Let's run our program once more. And here you can see the different elements. It seems that for our business to be profitable this year, we need to get 117 chocolates casted with the mold A, 133 with the mold B, 118 with the mold C, and 106 with the mold D. It makes sense that the mold D is the one that has the lowest value because it's the one that occupies the biggest amount of chocolate given in milliliters. And this is the KnapSack problem.